Next, we're going to talk about some practical issues in modeling contact. And the first one is these master-slave pairs. Theoretically speaking, there is no distinction between the two surfaces of the two bodies coming into contact. However, numerically speaking, we separate the roles for the two surfaces. We call one surface or one body to be the master and the other one to be the slave, and they have different roles in the contact algorithm. So the master surface is used to enforce constraint, while the slave surface is used to detect contact. Basically, the nodes on the slave surface is constantly looking for whether the contact is active or not. So this node would detect that now it's coming into contact with this edge on the master, and then the master node would then impose the reaction force to prevent this node from coming into the body of the master. Because of these different roles that the two body plays, we could have a situation where the master nodes go into the slave body like this. This is because the reaction force is only coming from the master towards the nodes of the slave, and when the master nodes, for instance here, if this node is undetected by the slave node here, then it could very well go into the slave body. A better approach is to use a different search algorithm where we have a group of nodes. For instance, we have a group of slave nodes searching together for whether contact is active or not. Then we have a less chance of having this kind of interpenetration. So some rules of thumb in deciding which surface should be the master and which should be the slave. First one is the rigid or stiffer body should act as a. Then the larger body should be the master, because so if you have the smaller body as a master, what would happen is that since the slave nodes are actively searching for contact, the slave nodes could very well miss the master nodes on the edge. And then the causal mesh should serve as a master to prevent these kind of things from happening. So if you have a final mesh as master, then you could very well have nodes undetected by the slave surface. Another suggestion is to use element-based surfaces, which means that these surfaces contain both nodes and edges and faces. They have more information. It's sort of a net instead of node-based, which only contains nodes. And then once you have these element-based surfaces, you can use them to form contact pairs. And these quantities would help to prevent this kind of outlier nodes that goes unconstrained. The second practical issue that I would like to talk about is about the mesh and element type. In contact problems, the pressure distribution is very sensitive to mesh size. Basically, the rule of thumb is that you want your element size to be smaller than the radius of your contact. And this makes sense because here you would expect a very high stress concentration. So this is a general rule of thumb. Whenever you have an area where stress is concentrated, you should use elements of size smaller than this size of the stress concentration area. Contact pressure is also sensitive to curvature. The smoother curvature would give a smoother distribution of pressure. Most of the cases, this is the physical situation. However, if we are using finite element to reproduce such a scenario, and linear elements would create artificial corners. They are not smooth enough, and hence your stress distribution could have artificial kinking or stress concentration or even singularity. What you can do is to use higher order elements so that you have a smoother curvature and hence a smoother stress distribution. Then there is another issue about size of increments. In the actual implementation of contact algorithm, the activation of contact depends on the tolerance. When a body comes close enough to a surface determined by a certain tolerance, this node would start to activate contact algorithm. And usually this tolerance is a certain percentage of the element size. For instance, 1% of element size. Basically a small enough quantity to prevent excessive interpenetration. So ideally, you want your increment to be small compared to this tolerance, so that you have a gradual approach to contact. If your increment is too large, then what may happen is that within one increment, the whole body is already inside and misses completely the tolerance range. A still undesirable situation is that the increment size could lead to excessive interpenetration. And there the solver would have difficulty converging, because before the increment there was nothing, and then right after one increment you have suddenly a very high reaction force on these nodes. The solver may not be able to find the equilibrium position for these nodes within the maximum number of iterations. And with respect to the penalty method, we could have ear conditioning if we use excessively large penalty stiffness. So here, this is the stiffness matrix for two element cases. If we have four elements, now we have a mid node on both sides, and when they come into contact, the reaction forces are only applied on the U2 and U3, and U5 and U6 they are still free. So we can have, you can try it yourself. So eventually you will have a larger stiffness matrix with 4 free degree of freedoms. You have the additional U5 and U6, and you have this matrix appearing in the middle of this larger stiffness matrix, and you have these additional terms. The factor of 2 is present because this node is shared by 2 elements, and similarly for this node. Now on the right we have the usual loading by displacement. When epsilon is very large compared to the rest of the terms, the stiffness matrix becomes so-called ill-conditioned. This is also the case when you have, let's say, 2 different materials for the 2 bars, and if one of the stiffness is much larger than the other, then you could have some of the terms having very large stiffness and, compared to the rest of the term, and then you still have a very ill-conditioned stiffness matrix. So in summary, today we have covered the wake form for contact problems, and we have covered the gap function, which is used to detect the gamma c, which is the contact area. And this gap function and gamma c, they are functions of displacement solution U. And we talk about the normal and tangential direction constraints, and the penalty method, which is an approximate method where a certain degree of interpenetration is allowed. And the good thing about the penalty method is that we do not have any additional unknown, and it's very easy to implement. However, we need to be careful with the penalty stiffness. Stiffness it cannot be too small, so then we have excessive overclosure or penetration. It cannot be too big, otherwise we have a ill-conditioned matrix. So this takes a lot of experience to decide what's the best parameter for penalty stiffness matrix. And then we have a Lagrange multiplier method. It's an exact method which enforces the constraint equation strictly, but it's an augmented system with additional unknowns. Then we've given a simple truss example to illustrate the penalty and the Lagrange multiplier method. And finally, we've talked a few practical issues.